Hello everyone, today we're going to be talking about exponential functions in the graph, section 7.1. So defining exponential functions, graphing exponential functions, and solving exponential equations. So everything we've been dealing with so far has x down where we can manipulate it next to the coefficients. But now we're going to talk about x being an exponent. So for exponential functions, let a be a specific positive real number that is not 1. The exponential function with base a is the function. And so here we have an example of f of x equals a to the x power. A is our base. So here's some examples. X to the second power, h of x equals 0.7 to the x power, so it's a decimal to an x power. Here we have g of x equals 1/3 to the x power, k of x equals the square root of 5 to the x power. Normally we wouldn't write this like this. We would write this like 5 to the 1/2 all to the x power, which we just write as 5 to the x over 2 power. So it'll be a fractional exponent. It's easier to see that. This looks kind of bizarre because it wouldn't matter if the x was inside or on the outside, but it's kind of hard to tell where you want it. Do you want it as superscript here or put to the square root, etc. And remember, this right here, this is automatically understood to have an index of 2, your square roots. And if you have if your function has one term that has an exponent, in it, an unknown, and an exponential slot, then the whole thing is an exponential equation. All right. So complete the following table and graph the function. So we're going to plug in some values for x to the 2 to the x power. So we know what 2 to the first power is. That's just going to be 2. Then we get the following where we have 2 to the second power. So this is 2 to the first, 2 to the second. That would be 4. 2 to the third would be 8. Over here, if it's 2 to the negative 1, we take the reciprocal, so that's going to be 1/2. This is going to be 2 to the negative 2, which is going to be 1/4, and this is going to be 2 to the negative 3, which is going to be 1/8. So you can see how we took the reciprocal of these numbers. Now it's interesting what happens here at 0. Well, it turns out that anything to the 0 power other than 0 is going to be 1. And we'll see more of that when we graph it. And then we have 2 to the 1/2, and that's an irrational number, so usually you just write that as a square root of 2, or 2 to the 1/2. So now we're going to graph this. And notice all the numbers are positive here. So when I graph this, I don't really need to worry about the negative portion here for this graph. But all my numbers are positive because there's no power I can raise 2 to that will make it negative, or 0 for that matter. So I'm going to mark off negative 3, negative 2, negative 1, 1, 2, and 3. And then I'm going to mark off 1, 2, 3, 4, 5, 6, 7, 8. So here I'm going to have my graph. And I'm going to have 1/8, which is really close to the x-axis. 1/4, still really close. 1/2, a little bit better. And then I'm going to have at 0, I'm going to be at 1. And then at 1, I'm going to be at 2. At 2, I'm going to be at 4. And at 3, I'm going to be at 8. And so you're going to see this graph, and it's going to curve up. And then it's going to increase very rapidly. By the time you're out to 10, you're over 1,000. By the time you're out to 20, you're well into the past the billions. So it increases very, very rapidly at a hence the name exponential. Excuse me, that's my phone. Sorry, somebody wants to help put the kids to bed, so I'll make this. I want to finish this video for y'all first, though. Get that out. Try to find a quiet moment in the day wherever you can. So next we'll look at the other graph. So here we're going to say, we already said anything to the 0 power is going to be 1. This is 3 to the first power, which is going, oh, this is to 1/3, excuse me. My mind's somewhere else. Let me start over. Let me find an actual pen that I like. This one's dying on me. Excuse me. Hope y'all didn't see that. That was bizarre. All right, so let's start again. We have 1/3 to the 0 power, which is 1, 1/3 to the first power, which is 1/3. Then we're going to have 1/3 to the second power, which is going to give me 1/3 times 1/3, which is 1/9. Then we're going to take the reciprocal of these, so we're going to have 1/3 to the negative first power, which is going to give us, can you also read that? Which is going to give us 3, and then 1/3 to the ninth power, or sorry, to the negative second power, which gives us the reciprocal of 1/9, which is going to be 9. So we're going to graph this. Very similar before. There's no number I can raise this to make my number negative. So I'm going to be on above the x-axis here. I'm going to mark out 1, 2, 1, 2, -2, -1, 1 and 2, and then I'm going to go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 2, we're at a 9th. I'll do this in different colors so you can see it. We're at a 9th. Then we're at a 3rd. Still pretty close. 0. We're at 3 here at -1, and then at -2, we're up here. And so it's pretty much the same shape, just going in the other direction. So we're going to have these rules. Let's see these on the next page. Here we're going to talk about the domain and range real quick. It's important to note that even though we have evaluated the exponential function for specific values of x, they are actually defined for every input. The domain is all real numbers. You can raise any base to any power, you get a real number back. Well, not any base. You can raise a valid base to any power. And the base is going to have to be greater than 0, not equal to 1. We cannot, however, have an output that is not a positive number. In other words, the range is from 0 to positive infinity, or your y values have to be greater than 0. This is in your set builder notation. So here, for when we have x, a, our base, is greater than 1. So the graph of the functions follow the form if f of x is equal to a to the x, follow the rules when a is greater than 1, then the point -1, 1 over a, 0, 1, and 1a will always be on the graph. Because the range is 0 to infinity, the graph can't go below the x-axis. The graph will increase or go upwards from left to right. So here we have, actually these are labeled incorrectly. This is supposed to be x to the third, and this is supposed to be squared over here. The third power is going to increase more rapidly than, 3 to the x power is going to increase more rapidly than 2 to the x power. So let me say this first line right here. I want to do it in different colors. So this first line, the purple line, is going to be y equals 3 to the x. And this blue line right here is going to be y equals 2 to the x. Right here, when a is between 0 and 1, in other words, when you plug in -1, you're going to get the reciprocal again, but this time it's not going to be a fraction. It's going to be, or it's not going to be smaller than 1. It's going to be greater than 1 because of the reciprocal. You're going to have 0, 1 still, and a 1. So all these points stay the same. It's just that a is going to be a fraction in this case, or in a fraction, well, less than 1, a decimal, less than 1. And then so because the range, once again, is between 0 and infinity, it can't go below the x-axis. It will decrease from down from left to right. So once again, this is going to decrease. So we're going to have this one right here. So this is actually going to be, you plug in -1, this is actually 2, and this is 3. Once again, cut and paste will get you every time. Whoops, it's supposed to go up. And that's going to be the denominator's 3. So correct those on your screen, or your keys, or your notes. That's what I wanted to say. It's too late to me making these videos. Exercise 3, sketch the basic graph. Determine the transformation necessary to obtain the graph from the function from the basic graph. Draw the graph, write the domain and the range of the function. So here, real quick, we can make the notes that this is going to be, as we move left to right, it's from left to right, it's going to be decreasing. And from left to right. And then also, we're going to move up 5 units. Then here, oh, they want the domain and the range. The domain for this is going to be it's going to be from negative infinity to positive infinity as before, but the range, which before started at 0 and went to infinity, that infinity is going to stay there, but it got moved up 5 units, so it's going to start at 5 instead of 0. For this one, as we move left to right, what's going to happen is this is actually going to, normally it would increase as you move left to right, but here, since it's upside down, because that's negative, as we move left to right, it's going to decrease, but it's going to be upside down, because it's negative. So it's going to be reflected. Across x-axis, and that's what flips it over. And then this one is going to be moved 1 unit up, and then also it's going to have a domain, going to be negative infinity to positive infinity like the other one, and the range, well, before it was from 0 to infinity, but this is going to be reflection, so it's going to start at negative infinity, or it's going to start on negative infinity of the y-axis, and then the maximum y value, since it's upside down, would be 0, but now we're going to move it up 1, so it's going to be 1. So that's just to keep track of that. So let's go graph these real quick with those pieces of information. So when graphing these, there's a couple ways we can do it. We could keep track of the original graph. So you have the original graph that's going to be decreasing like this. And then we just move it up 5 units. So instead of crossing at 1 here, it's going to cross up here. Instead of crossing at 1, it's going to cross at 6. And the maximum value, or the minimum value it's going to have is 5. But I tell students usually what's easier is to try to make this a nice number to graph and then graph it that way. Because Hawks will often have you compare graphs. So if you pick nice x values, like if I pick x equals -1, well, let me actually make an xy table for that. If I pick a nice value like x equals -1, then this becomes 1/2 to the negative first power plus 5. So that's going to give you 2 plus 5, which is 7. And then you can always plug in 0 because it's going to give you 1 back out, 1/2 to the negative first power, or negative 0, or sorry, just 0 power. 0 power. And plus 5 is just going to give you 6 back out. And so you get two nice numbers. You can kind of see what your graph's doing. So here we plug in -1. And we got 1, 2, 3, 4, 5, 6, 7 back out. And then we're going to plug in 0, and we get 5 back out. No, 6 back out, excuse me. And then the minimum value we said we're going to have is going to be at 5. So we're going to have this graph that's going to come in, and then it's going to flatten out right here. And so this is our graph right here. So Hawks will give you a multiple graphs to pick from on your homework. And so you just have to really match up 2 good points to your graph. And so where it crosses the y-axis is a good one when you plug in 0. And then 1 point to the left or the right is usually a good one to pick as well. Once again, our increasing, moving up, 5 units, domain, range, we all found that earlier. But you can look by the graph. The range is maybe easier to find with the graph right here, knowing that this would be 5, be 6, and this would be 7. All right, so next. So this is going to be reflected, so it's going to be underneath the x-axis, part of it anyway. And so once again, I always suggest students to plug in nice numbers and get nice numbers back out. Be somewhat consistent. And so nice numbers to plug in would be like 0, because if I plug in 0, I'm going to get 1 minus 3 to the 0 power, which is going to give us, 0 back out. And then we plug in 1, we're going to get 1 minus 3 to the first power, which is 1 minus 3, which is going to be negative 2. And then I may get another point back out just to be sure that I'm on the right, it's shaped the right way. And you can plug in 2, and we get 1 minus 3 to the second, which is going to be 1 minus 9, which is going to be negative 8. So here we can say we're going to cross at 0, 0, so we're going to be there. We're going to go over 1 and down 2. We're going to go over 2 and down 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to have 0. I'm going to have 1, negative 2, and then I'm going to have 2, negative 8. Right here. So it would have normally been an exponential. So the smallest value you could possibly get, if this is a very, very large, this is a very, very small, or sorry, very large negative number. It's something on the left. We could almost get this to 1. You'd have a horizontal asymptote right here at 1. You could almost get it to 1. So it looks something like this. Assuming I could hit my dots. And so it'd be this graph that was originally, so the original graph would look something like this. Oh, I should use a different color. The original graph would have looked like this. Oops. And then we'd reflect it across the x-axis, and then we move it up 1 unit. So we'd have this purple line right here. Once again, we can see that our domain and range, our domain was all real numbers, and our range is going to be from negative infinity, that's our lowest y value, to our highest y value in this case, which would be 1. Next, we're going to have solving exponential equations, which is probably the most useful portion of this lesson. This is actually kind of interesting because basically it's everything we've ever done before with polynomials, only now our polynomials are going to be exponents. And so we're going to solve, when we solve our linear equations, our polynomials, we're just doing them for exponents. So it's just an extra step. And so, solving exponential equation is an equation with variables and the exponents. To solve these, we rewrite both sides of the equation with the same base, set the exponents equal to each other. If a to the x equals a to the y, then x has to equal y. So it's saying if your bases are equal, your exponents have to equal. You can kind of think of them as canceling, and you get x equals y. That's not really what's going on, but students like to think that. You can think that for now. We'll correct it here in a lesson. Solve the equation that results. So we want to solve the following equation. So we want to get the same base. So I'm going to rewrite this 2 to the x equals 2. Well, what gives me 8? 2 to the third. So that means that x must be 3. Because I can kind of think of these as canceling. It's not really what happens. We'll learn how they happen here in a little while, but we kind of can think of these 2's canceling, so I just get x equals 3. The bases are the same. The exponents have to equal. So now we're going to redo this. 2 is not a power of 8, but 8 is a power of 2. We saw that before, so we're going to say 2 to the third, all raised to the x power, gives us equals 2 to the x plus 4. So I'm going to raise a power to a power. When I raise something to a power that's been raised to a power, I'm going to get 2 to the 3x equals 2 to the 2x plus 4. So when I rewrite this, and I kind of think of these 2's as canceling, I'm going to get 3x equals 2x plus 4, and that's going to give me, bring the 2 to the other side, subtract 2x from both sides, and I'm going to get x equals 4, and we're done. And remember, you can always check this. You can always say 8 to the 4th power has to equal 2 to the 8 plus 4, what we're looking at, which is going to give us 2 to the 12th has to equal 2 to the 12th, which checks out. This one's a very interesting one right here, because right here, if you look at this, there's no way 0.5 looks like it's a power of 5. But when you're stuck, always rewrite this as a in terms of a fraction. So when you start, you say 5 to the x is going to equal 4 over 100. Or sorry, that's actually, this is incorrect. This is written incorrectly. This is supposed to be 0.04. Otherwise, it doesn't make any sense. That decimal is in the wrong place. Excuse me. Typo. One of these things I need to every year. I'm going to correct this lesson, and then I teach it anyway. I'm going to teach it because it matches your current notes. Teach it this way. Maybe I'll correct it for next year. So you have 0.04 is what it's going to equal. So forget that. 0.04, and so it doesn't look like it's going to be a power of 5, but then if you say 5 to the x equals 4 over 100, well then that's 5 to the x equals, if you reduce this, 4 goes into 125 times, so it's 1 over 25. 1 over 25 is actually 1 over 5 squared, which we can rewrite that as 5 to the x equals 5 to the negative second power, which means that x has to equal negative 2. That's our answer there. So it's all about getting the same base. Later on we'll learn if you can't get the same base, how we solve those with our logarithms. Once again, we just have interesting equations here. So we have to get the same base, and we notice here that we can't do that. Well, we have to get the same base. We notice that 27 is not a power of 9, not a whole number power of 9. But 9 and 27 both have 3 in common as a base. So I could say this is going to be 3 to the second all to the x power equals 3 to the third all to the x plus 2 power. It's really important that you put this x plus 2 in parentheses, because that power, 3 to the third power, is it doing the focus thing? Or not. I need a better camera. 3 to the 2x equals, and now we're going to have 3 to the 3 times x plus 2, because that 3 belongs to the entire x plus 2. So now I have the same base. Well, let me finish the math and the exponents first. 3x plus 6. If you don't do that, you're going to miss that plus 6 there. And so I'm going to have 2x now equals, so this is where I apply my rule, where I have, a to the x. It was kind of easy to see where that happened earlier. A to the y. This is my x equals y portion right here. My 2x is now going to equal 3x plus 6. I move the 2x to this side and the 6 to the other side, and I'm going to get negative 6 equals x, or negative x equals 6. And once again, you can check that. This one's a little interesting. Right here, it looks like, wait, 7, is that a power of 1? And actually, everything's a power of 1. I mean, anything to the 0 power, or sorry, any number has to the 0 power is 1. So 1 can always be written as your base to the 0 power. So now it makes sense. So now you can say we have 7 to the x squared plus 3x equals 7 to the 0 power, which is equal to 1. I should say that's equal to 1, not cross that out. So now we're going to say that's going to be x squared plus 3x equals 1. So that's going to give us x squared plus 3x minus 1 equals 0. And now we go to solve this. And so when we solve this, it's not going to come out. No, I'm sorry, it's 0. What am I saying? I got myself confused. I had to set my exponents equal. This is 0. I'm like, that wouldn't work out. Let me start over again. All right, trying again. So we set this, so that means we're going to have x squared plus 3x equals 0. And then, not 1, because that's the power it is. 7 to the 0 power gives us 1. So now we're going to have factor out that x, and so we're going to have x times x plus 3 equals 0. So that means x equals 0, or x plus 3 equals 0. So that means x equals negative 3. So we have two answers for this one. And that's pretty apparent because it's quadratic. So x could be 0, x could be negative 3. So it's just like solving polynomials, only they're an exponent, so we just have to do that additional step of getting the bases the same. One other thing I wanted to show you is that you may see it written a little bit differently. You may see something to the effect of 5 to the x minus 2 minus 1 equals 0. And so you move that 1 to the other side, and you'll have 5 to the x minus 2 equals 1. And so now you're going to say 5 to the x minus 2. I'm just making this example up. You don't have it in your homework or on your notes. It's the 5 to the 0 power. So I might have this additional step moving the negative 1 to the other side so you can get the bases the same. And basically you're going to say x minus 2 equals 0. So x equals 2 in this case. So you may see it written, this problem written a little bit differently with the 1 on this side and being subtracted. So look out for that as well. Sometimes they change it up a little bit. All right, so that's everything for this lesson. Y'all have a great day.